basics of corrosion, mechanism and its control. So I am Dr. P. Rameshkumar, Assistant Professor of Chemistry, PSN College of Engineering and Technology, Tirunelveli. So corrosion is the gradual destruction of metals by means of chemical or electrochemical or biochemical reactions with the environment. So during this process, the metal will be converted, metal zero will be converted into the oxidized states of metal. So it's a quite a reverse process of metal extraction, where the higher oxidized state of metal will be converted into metal with the zero oxidation state. So naturally metal occur as their oxides, sulfides, carbonates. So as we already know, so the chemically combined state is thermodynamically more stable. That's why they present as the compounds of metals, such as oxides or sulfides or carbonates. So these are the combined state. Combined state is the thermodynamically more stable state. So in which metal will have the +1 or +2 or +3, +4 oxidation states, other than zero oxidation state. So when we extract a metal from its ore, the metal is in a higher energy state, so which is thermodynamically unstable one. So as we already know, metals are highly electropositive. So metal with the zero oxidation state is high energy state, so it will try to go back to the combined state or oxidized state by means of chemical or electrochemical interaction with the environment. So this is the difference between corrosion and the extraction of metal. Corrosion, in which metal with zero oxidation state will be converted to metal with higher oxidation states. So in extraction, metal with the higher oxidation state will be converted to metal with the zero state. So of course metal with the higher oxidation state or combined state is the thermodynamically stable state. That's why they are present as the compounds of corresponding metals, other than metal with the zero oxidation state. So this is a quite interesting process. We will see the basics of the corrosion process and the one of the corrosion control methods, that is cathodic protection method. So normally every country spends a lot of money on the corrosion related issues. For example, maintaining the instruments or boilers, or spending more money on protective coatings. So that's why in that way this topic is very important in day-to-day life. So these are the effects or consequences of corrosion. That's why we need to give much focus on the corrosion related issues. So efficiency of the machine will decrease, plant will be shut down due to failure, the products will be contaminated, toxic products of corrosion will cause health hazards. So there is a necessity to go for alternative designs and protective coatings, so in order to avoid the corrosion process on the metals. So a lot of consequences are there. So here we present important consequences: the efficiency and product contamination, health hazards, and goes on. Classification of theories of corrosion. So corrosion can be classified into two major categories. One is dry or chemical corrosion. The second one is wet corrosion or electrochemical corrosion. So in dry corrosion, which does not involve the moisture during the course of the corrosion process. So it is based on the attack of the chemicals, for example atmospheric gases like oxygen, sulfur dioxide, hydrogen sulfide. Okay, so the dry corrosion is occurring due to the attack of these chemicals on the metal surface. So for example, tarnishing of silver by hydrogen sulfide. So again we can classify the dry corrosion into three major classes: oxidation corrosion, second corrosion by hydrogen, third liquid metal corrosion. So this corrosion does not involve moisture or water molecule. So only the attack of the chemicals causes corrosion on the metal surface. So what is oxidation corrosion? Simply we can say it is the direct attack of oxygen on metal surface which will lead to the corrosion of material or destruction of metals. So it is due to the direct attack of oxygen on metal surface in the absence of moisture. Okay. So alkali and alkaline earth metals are corroded at low temperature. At high temperature, most metals except gold, platinum and silver are oxidized. So at low temperature, the metals present in alkali and alkaline earth groups will get oxidized. At high temperature, most of the metal will get oxidized except the coinage metals or noble metals like gold, platinum and silver. So what is the mechanism involved in the oxidation corrosion? So when the oxygen attacks the metal surface, there are two processes. One is oxidation of metal surface into metal with higher oxidation state. Oxidation of metal 0 will be converted to, or the metal with 0 oxidation state will be converted to metal with higher oxidation state. It is called oxidation of metal with the release of the corresponding electrons. So for example, if the metal forms 2 plus oxidation state, so 2 electrons will be evolved. These 2 electrons will be captured by the oxygen atom in order to get converted into oxide ion, O2 minus. So there are oxidation and reduction reactions. Oxidation in which metal 0 will be converted to metal with higher oxidation state. Reduction during which oxygen will absorb these 2 electrons released from the above oxidation reaction, so will be converted into oxide ions. So these 2 ions, positive and negative ions, will combine to form the respective metal oxide. So if it is a metal with 2 plus oxidation state, it will combine with the oxide ion O2 minus, will give the metal oxide. So what is the consequence of this process? Metal surface will be converted into monolayer of metal oxide. So further corrosion is possible by the diffusion of metal ions through the oxide layer, through this they already formed metal oxide barrier. So growth of oxide film is always perpendicular to the metal surface. So we can easily understand from this picture. So this is you consider as the metal. So this surface is prone to get oxidized during the attack of oxygen. So once oxygen attacks this metal surface, metal 0 is converted to metal 2 plus. At the same time, the 2 electrons is captured by the oxygen molecule to form oxide ion. So these 2 ions combine to form metal oxide at the surface of the metal surface of the metal. So this is the metal oxide interface. This is, you could say, metal oxide film. So depending on the metal or depending on the nature of metal oxide, the further growth will occur. So growth of metal oxide is based on nature of the metal oxide and nature of the metal surface. So this is the oxygen environment. Okay, so this is a simple mechanism occurring at the oxidation of metal surface. So we can classify the metal oxide films into various types based on the Pilling-Portworth rule. So whether if we can say that the metal oxide layer is porous or not porous based on the volume of metal oxide formed. So Pilling-Portworth rule says the ratio of the volume of oxide formed to the volume of metal consumed is called Pilling-Butterworth ratio or Pilling-Butterworth rule. So Pilling-Butterworth rule is the ratio between the volume of oxide formed and the volume of metal consumed. So we will look at, so what would be the nature of the metal oxide layer if the volume of metal oxide layer is higher than the volume of metal consumed or lower than the volume of metal consumed. So what will be the nature of the metal oxide layer, that we will see now. So if the volume of oxide layer formed is less than the volume of metal consumed, the oxide layer is porous. Means that the volume of metal oxide layer is lesser when compared to the volume of metal consumed. So in that case we can say the oxide layer is porous. Oxide layer is porous means the further corrosion is possible. Through that pores, again the oxygen molecule can interact with the metal surface, so that the corrosion will be continuous. So volume of metal oxides of alkali and alkaline earth metals are lesser than the volume of metal consumed. So the oxide layer is porous and non-protective. So it cannot protect the metal surface further. So it will encourage the oxygen molecules to get involved in further corrosion. So in the opposite case, in the reverse case, if the volume of metal oxide formed is greater than the volume of metal consumed, then the oxide layer is non-porous, so it will be acting as the protective layer. Why? Because the oxide layer the volume of oxide layer is much higher than the volume of metal consumed. So the layer is called non-porous. So if it is a non-porous layer, further corrosion is not possible, because it will prevent the interaction of oxygen with the metal surface. So for example, the volume of oxides of heavy metals such as lead and tin are greater than the volumes of the metal consumed. So the oxide layer is non-porous and protective. So this type of layer will be acting as the protective layer. So metal structure will be protected, no more further corrosion. So again we can say it is a stable oxide layer. A stable oxide layer is means strongly absorbed on the metal surface. The layer is impervious and prevents further corrosion. So the layer itself acting as the protective layer. So if it is non-porous, it will be acting as the protective layer. Further corrosion is not at all possible at the metal surface. Example, oxides of aluminum and copper. These are some of the examples. So again, unstable oxide layer. So once it is formed, it will be destroyed immediately, or it will be decomposed. It will be decomposed as soon as it is formed. So this is mainly produced on the surface of the noble metals, for example silver, gold and platinum. So these unstable oxides decompose to stable metal and oxygen. So these are the coinage metal, noble metal. Noble metals always try to be in the form of zero oxidation state. So whenever the oxide film is formed, immediately the oxide layer will be decomposed in order to form the stable metal, meaning a metal with the zero oxidation state and the oxygen molecule separately. So this type of layer is called unstable oxide layer. This happens at the surface of the coinage metals or noble metals. So metal oxide, as soon as it is formed, it will be converted into pure metal plus oxygen molecule. So one more oxide layer is there, that is called volatile layer. The oxide film volatilizes as soon as it is formed. So for example, molybdenum oxide, molybdenum MoO3, molybdenum oxide. So once it is formed, it will immediately volatilize, leaving the metal surface for further corrosion. So it leaves the fresh metal surface for further continuous attack. So this also, in this case also, the corrosion process continues, because volatile oxide layer easily volatilizes as soon as it is formed. So again the metal surface will be exposed for the further attack. So based on the Billing-Bentworth rule, we can classify whether the metal oxide layer is porous or non-porous, and again the oxide layer can further be classified into stable oxide layer, unstable oxide layer and volatile oxide layer. So this is the mechanism and various types of oxide layer formed during the oxidation corrosion. So oxide layer mainly depending on the metal surface. So nature of the oxide layer depending on the nature of the metal surface. So simple mechanism: formation of metal ion and the formation of oxide ion. Combination of these two ions will form the metal oxide layer. So based on the metal surface, we can classify the metal oxide layers into different types. Based on the Billing-Bentworth rule, we can say whether it is porous or non-porous layer, or non-protective and protective layer, then unstable layer, stable oxide layer and volatile layer. So second chemical corrosion or dry corrosion is corrosion by hydrogen. Corrosion due to the presence of hydrogen gas. So what is hydrogen embrittlement? The loss in ductility of a material in the presence of hydrogen is known as hydrogen embrittlement. The corrosion due to the presence of hydrogen gas is called hydrogen embrittlement. So during this process, what will happen when hydrogen sulfide interacts with the iron metal? So there will be a formation of iron sulfide plus atomic hydrogen. So this atomic hydrogen will enter into the voids present in the iron metal. So where it will be collected as the hydrogen gas. So in the voids, so when the pressure of the gas increases, there will be a cracks formation in the metal surface. So what is the first step? In the first step, hydrogen sulfide gas interacts with the iron metal, so it will form atomic hydrogen. So this atomic hydrogen diffuse into the metal matrix and gets collected in the voids present in the metal matrix, surface of the metal, inside the metal. So when the concentration of the hydrogen gas increases, pressure also increases, which will lead to the cracks in the metal surface. So this is called hydrogen embrittlement. Cracks formation due to the presence of hydrogen gas is called hydrogen embrittlement. So when the pressure of the gas increases, cracks and blisters develop on the metal. A simple mechanism. Then decarburization. The name itself says decarburization, meaning the removal of carbon from the metal structure. For example, if you consider steel always contains particular percentage of carbon. Okay, so if you remove this carbon from the metal structure, so that will lead to the formation of cracks inside the metal. That is called decarburization. So we will see now. So it is a process of decrease in the carbon content of the steel. So it is the process of decrease in the carbon content of the steel, which means during the process carbon is removed. So that's why it develops a cracks inside the metal. At high temperature, molecular hydrogen decomposes into atomic hydrogen. So molecular hydrogen H2 will be converted into H, atomic hydrogen at high temperature. So this atomic hydrogen will combine with the carbon present in the steel to form methane gas. So wherever gas forms, the increase of gas content leads to the increase in pressure of the gas, so which further leads to the formation of cracks inside the metal. Okay, so as like hydrogen embrittlement, here also there is a formation of gas. In hydrogen embrittlement, the cracks due to the formation of hydrogen gas. Here, in decarburization, the cracks formation due to the development of the formation of methane gas because of the reaction between carbon and hydrogen. So when steel is exposed to this environment, when steel is exposed to the hydrogen environment, carbon in the steel reacts with the atomic hydrogen to form methane gas. So once the methane gas collected in voids of steel, which develops high pressure, leading to the cracking in the metallic structure or iron surface. So far we have seen three types of two types of chemical corrosion. One is corrosion by oxygen, corrosion by hydrogen. So in corrosion by hydrogen there are two types. One is hydrogen embrittlement, second one decarburization. So that dry corrosion is liquid metal corrosion, where the liquid melt penetrate into the solid metal, which causes corrosion at the solid metal surface. This is called liquid metal corrosion. So when the liquid metal or liquid melt travels through the solid material or solid metal, there will be a dissolution of solid metal, which is called liquid metal corrosion. So here it is given as it is due to the chemical action of flowing liquid metal at high temperature, which involves dissolution of solid metal by a liquid metal. Second, the penetration of liquid metal into the solid metal. Just by penetrating the liquid metal into the solid metal, causing the corrosion at the solid metal surface, which is called a liquid metal corrosion. The second major type of corrosion is wet or electrochemical corrosion. In dry corrosion, moisture ready to involve during the process. So in the wet corrosion or electrochemical corrosion, there will be involvement of moisture or water molecule, or you can say some liquid electrolyte solutions. So when two dissimilar metals or alloys when in contact with each other in the presence of aqueous solution, this type of corrosion occurs, electrochemical corrosion occurs. Or when the metal is exposed to the electrolyte with varying amount of oxygen, so there is a possibility of having the wet or electrochemical corrosion. So when two dissimilar metals or alloys in contact with the moisture, so there is a possibility of having wet corrosion. And another one, when the metal is exposed to particular electrolyte with different concentration of oxygen, this type of corrosion occurs. So now we will look at step-by-step mechanism of electrochemical corrosion. So in the first step, metal dissolution occurs at the anode. So in electrochemistry, we already know that the oxidation occurs at the anode and the reduction occurs at the cathode. The anode, which one acting as the anode and which one acting as the cathode, that is based on the electrochemical series. The metal having low standard reduction potential will undergo oxidation when it is connected to the other metal having higher reduction potential compared to the previous one. The metal having higher reduction potential will undergo the reduction reaction. So when it is connected or when it is made alloy. So metal dissolution occurs at the anode. Oxidation involves conversion of metal 0 into metal N plus with the loss of or with the release of an electron. So reduction reaction occurs at the cathode, that is based on the environment. That is based on the surrounding environment. If the environment is acidic, there will be a evolution of hydrogen. So these electrons coming from the anode will be attracted towards the H plus ions, or the H plus ions combines with the electrons released from the anode to form hydrogen gas. So this type of corrosion is called hydrogen evolution type. If the environment is acidic, the corrosion is called hydrogen evolution type corrosion. So if the environment is neutral environment or slightly alkaline medium, so there will be a formation of hydroxide ion. So we can otherwise say it is an oxygen absorption type reaction. Oxygen absorbs the electron released from the anode to form hydroxide ion. So in the mechanism anode reaction is same whether it is acidic environment or neutral environment, but cathode reaction is different. If it is an acidic environment, there will be evolution of hydrogen. If it is a neutral environment, there will be evolution of, or there will be a formation of hydroxide ion. So this is the example of hydrogen evolution type corrosion. Anode reaction will be same. Here iron metal is taken. So iron is converted into Fe2 plus 2 electron. So this reaction is this corrosion is occurring at the acidic environment like hydrochloric acid. So generally all metals above hydrogen in the electrochemical series will dissolve in acid, consequently producing hydrogen gas. Okay. So here we have taken hydrochloric acid, which is the non-oxidizing acid. So in acidic environment, the iron will be converted to iron 2 plus 2 electron. So these 2 electrons will combine with the H plus ions present in the acid to form hydrogen gas. So that's why we can call it as hydrogen evolution type corrosion. So this is a schematic pictorial representation of this hydrogen evolution type corrosion. So H plus Cl minus is there in the acid. So when the this is a acidic environment in which the iron metal is taken. So iron is converted into Fe2 plus with the release of 2 electron. So these 2 electron will combine with the H plus ions to form hydrogen gas. The second type is oxygen absorption type or the formation of hydroxide ion type corrosion. So which is occurring at the neutral or weakly acidic medium. So usually the surface of iron is coated with the thin layer of thin film of iron oxide, but if this thin layer is broken, the metal surface will be exposed to the environment. So the exposed surface will be acting as the anode and remaining part will be acting as the cathode. So when iron is in contact with the electrolyte solution in the presence of hydroxide ion, in the presence of oxygen, so there will be a formation of hydroxide. So when iron is exposed to the electrolyte solution in the presence of oxygen, this we can expect this type of corrosion, meaning there will be a formation of iron hydroxide. So here it is we can consider is a single metal, iron only, no galvanic type corrosion. But whichever the area is exposed to the environment, that will be acting as the anode. Remaining part will be acting as the cathode. So we can otherwise say based on the concentration cell corrosion that we will study later, the area exposed to the more amount of oxygen will be acting as the cathode. So we will see in the next lecture that different kind of corrosion. Okay, in this lecture we will study only the mechanism of the basic corrosion processes, dry and wet corrosion. So that surface, that cracked surface, the exposed surface due to the formation of cracks is acting as the anode, where Fe will be converted to Fe2 plus with the release of 2 electron, and at the same time the remaining part will be acting as the cathode, where oxygen is reduced to hydroxide ion. So these 2 electrons are absorbed by the oxygen molecule in the presence of water. So always we have to write in addition to electron we have to write water molecule, because this reaction is conducted in neutral or weakly basic medium. So there will be a formation of hydroxide ion. So if the Fe2 plus and 2 OH minus combine, it will form ferrous hydroxide, FeOH twice, ferrous hydroxide. So if more amount of oxygen is present, or if enough oxygen is present, so there will be a possibility to convert Fe2 plus into Fe3 plus. So FeOH twice is converted to FeOH thrice. So this is a further oxidation, Fe2 plus to Fe3 plus. So this product is called rust. It's a typical corrosion product formed at the surface of iron, that is called rust. So the overall reaction we can write for this oxidation reaction, FeOH twice plus O2 in presence of water, which gives FeOH thrice. So this rust product we can mention as Fe2O3 oxide, in oxide form also Fe2O3, where Fe will be in 3 plus form. In that case also Fe will be in 3 plus form, Fe2O3. So this is a pictorial representation. So wherever the crack forms, so this is already a oxide layer. So if crack forms at the oxide layer, this area will be exposed to the environment, that will be acting as the anode, and the remaining part will undergo reduction reaction. So based on the above process, we can two mechanisms we can differentiate chemical corrosion and electrochemical corrosion. So it occurs in dry corrosion, chemical corrosion occurs dry condition, and electrochemical occurs in the presence of moisture or electrolyte. So chemical corrosion, where direct attack of chemical on the metal by the direct attack of chemicals on the metal. Here the formation of large number of anodic and cathodic areas. Even homogeneous metal surface is corroded, only heterogeneous or bimetallic surface is corroded in electrochemical corrosion. Corrosion product gather at the place of corrosion. So here in electrochemical corrosion, corrosion occurs at the anode, but product can be formed in elsewhere in the corrosion system, that may on the surface of the metal. Corrosion occurs at the anode, but we can find the corrosion product at elsewhere. Dry corrosion is a self-controlled process. It is a continuous process. Electrochemical corrosion is a continuous process. It takes place by adsorption mechanism. Chemicals will be adsorbed first on the metal surface. In wet corrosion, it follows electrochemical reaction, anodic and cathodic reactions. So example of dry corrosion, mild scale formation of iron surface. In electrochemical corrosion, the formation of iron hydroxide, ferric hydroxide, that is called rusting, under moist atmosphere. So this is the fundamental differences of dry and wet corrosion. Then in this lecture we will see one of the methods of corrosion control called cathodic protection. So rate of corrosion can be controlled by modifying the metal or environment. The rate of corrosion can be minimized, or rate of corrosion reaction can be decreased by modifying the metal or the environment. So one of the important methods is cathodic protection, where the metal which we want to protect is made as the cathode. So from the previous slides, we come to know that corrosion always occurs at the anode side. So if you want to protect our metal, so we just made as the make our metal as the to be acted as the cathode. So corrosion will not occur at the cathodic part; it always occurs at the anode. So we forcefully made our material to act like a cathode. This is achieved in two ways. One is sacrificial anode method, another one is impressed current method. Impressed current method we will see after 2 or 3 slides. So now we will discuss sacrificial anodic method. Sacrificial anode means the metal, one metal is sacrificing its life in order to protect the original metal. So that is called sacrificial anode. So how to choose the sacrificial anode method? That is based on the electrochemical series. So there is a series, all the metal can be categorized based on their standard reduction potential. So if we consider the series as the top to bottom, the metals present at the top of the series will easily undergo oxidation. So they are acting as the anodes. And if you want to protect the metals from the bottom line, you just connect this metal with the other metal which is at the top of the series, or which is having less reduction potential. So here it is, some examples are given. In this method, the more active metals like zinc, magnesium, they are having comparatively lesser reduction potential than iron, are attached to base metal, that is cathode, which is to be protected from corrosion. So if we want to protect our material, metal, that metal should be connected with zinc or magnesium. So because zinc and magnesium having comparatively lesser standard reduction potential than our original metal, so probably we will take iron as our metal. If we consider iron, comparatively iron has the higher reduction potential. So if iron connected to magnesium, based on the reduction potential difference, magnesium will be acting as the anode. So automatically cathode will be protected. So these anodic metals being more reactive undergoes corrosion, but base metal remains unaffected. So this is called sacrificial anode method. The metals using for this type of protection is called sacrificial anodes. Here zinc and magnesium are called sacrificial anodes. So here the metal to be protected is made cathode by connecting it to a more active metal, that is called anodic metal, called sacrificial anode. Only the corrosion concentrates on the more active metal, so that our original metal will be protected. So I want to protect this pipe, probably it may be made up of iron. So I want to protect its structure, so that I just connect this metal with the other metals having lesser standard reduction potential than the original metal. So automatically the corrosion occurs at the magnesium or zinc, which is called the sacrificial anode. So the sacrificial anodes have to be replaced from time to time after complete corrosion. The method is used for buried pipeline, ship hulls, industrial water tanks. Several 100 kilometers long zinc wire is buried along oil pipeline in Alaska is the best example for sacrificial anodic protection method. So various applications are there. So as I already told, it applied in buried pipelines, underground cables, protection of ships and boats. Calcium metal is used to minimize engine corrosion. Magnesium sheets are inserted into domestic water boilers to prevent rust formation. So another cathodic protection method is impressed current method. Impressed current cathodic protection. So always wherever the corrosion occurs, there will be an electron flow from the anode. So due to which there will be a flow of current. So this current is called corrosion current. So what is impressed current? If the corrosion current is nullified with the external current or external power supply, that current is called the impressed current. The flow of electron will be reversed due to the presence of external power supply like battery. The corrosion current or the electron flow will be reversed, so that our original structure will be protected. So here an impressed current is applied in an opposite direction to nullify the corrosion current. That's what I told. In order to nullify the corrosion current, the external current is applied to reverse the flow of to reverse the direction of electron flow. Thus the corroding metal is converted to cathode from anode. The negative terminal of battery is connected to the metal to be protected. The positive terminal is connected to the inert anode. For example, graphite. The anode is buried in a black backfill containing a mixture of gypsum, coke, grease and sodium sulfate to increase electrical contact. So if you look at this picture, you can clearly understand. I want to protect this structure. So usually this is more vulnerable to get corroded. So in order to reverse the flow of electron, I just connect the external power supply, DC power battery. The negative terminal will be converted to my original metal structure, and the positive will be connected to the impressed anode, for example graphite. So now the electron cannot flow from the original metal structure. This flow will be reversed due to the presence of the external power battery. So the corrosion current will be reversed, or the electron flow will be reversed, so that the metal structure will be protected. So it is used in the protection of tanks, transmission line, power towers, underground water pipes, oil pipeline, ships, etc. So some of the limitations are there in impressed current method. So it is somewhat costlier than the sacrificial anode protection method, and it fails when the current is switched off. With the external power, when the current is switched off, so it cannot work. The corrosion current will be traveling from, or the electron flow will be from the metal structure, that is called corrosion. So when the power is switched on, the system works. So I wind up this lecture up to this slide. The remaining part of this interesting part, corrosion, interesting topic, corrosion, the various types of corrosion will be discussed in the next lecture. Thank you.